This is a continuation of Chapter 4, Direct Proof. So the first few proofs that we look at in this chapter are going to use the definition A divides B. So the definition is this: suppose that A and B are integers, then A divides B, written A bar B, if B is equal to A times C for some integer C. In this case, A is a divisor of B and B is a multiple of A. So let's just look at a few examples. So for example, is it true that 4 divides 24? So does 4 divide 24? And in this case, the answer is yes. The answer is yes because 24 is equal to 4 times 6. And 6 is an integer. Let's look at another example. So, for example, does 3 divide 20? And the answer to this is no. It's no because 20 is not equal to 3 times any integer. So there is no integer C such that 20 is equal to 3 times C. So to continue thinking about this definition, I'd like you to try thinking about for which integers A is it true that A divides 0? So for which integers A is it true that 1A divides 0? Also, for which integers A is it true that 0 divides A? 3, for which integers A is it true that 1 divides A? And 4, for which integers A is it true that A divides 1? So figure out which integers A fit each of those criteria, and we'll talk about it in just a moment. Okay, so for which integers A is it true that A divides 0? Well, A divides 0 if 0 is equal to A times C for some integer C. And observe that this is always true for any integer A because we can let C be equal to 0. And then, yes, it is true that 0 is equal to A times 0. So A does divide 0 for any integer A. That's right, for all A in the integers. Okay, so now when is it true that 0 divides A? Well, if 0 divides A, that's true if and only if A is equal to 0 times C for some C in the integers. And when is that true? Well, 0 times anything is 0, so that is only true when A is equal to 0. So only for A equal to 0, that is the only integer that makes that statement true. For part 3, 1 divides A if and only if A is equal to 1 times some integer C. But note that we could use C being equal to A, and in that case, A is equal to 1 times A, which is A, is always true, and A is an integer by hypothesis, so 1 divides A for any A in the integers. So finally, A divides 1 if and only if 1 is equal to A times C for some integer C. And this is true if and only if 1 over C is equal to A. And again, A is an integer, C is an integer. So this can only be the case if C is equal to 1 or C is equal to -1. And in this case, then A equals 1 or A equals equals -1. So these are the only values of a for which a divides 1. Okay, let's do a proof using this new definition. So let's prove the following proposition. Let a and b be integers. If a divides b, then a divides 2b squared minus 3b. Let's just put on scratch paper on the side what we are trying to prove. We want to show that a divides 2b squared minus 3b. We want to show that a divides 2b squared minus 3b. This is true if and only if 2b squared minus 3b is equal to a times some integer, say k, where k is an element of the integers. So that's what we are trying to show, and so we're going to keep that in mind while we're doing the proof. So proof, suppose that a and b are elements of the integers and that a divides b. So we've just stated the hypothesis and assumed everything in the hypothesis is true. Now let's expand the definition of what it means for a to divide b. So since a divides b, b is equal to a times c for some c in the integers. Now we're trying to prove something about 2b squared minus 3b. So observe that 2b squared minus 3b is equal to, using substitution, instead of b we can write ac squared minus 3ac. And that would then be equal to 2 times ac squared is a squared c squared minus 3ac. And we're trying to show that this quantity is equal to a times some integer k. So can we factor an a out? Yes, this is equal to a times 2ac squared minus 3c. We've factored an a out of each term, where 2ac squared minus 3c is an element of the integers. And so, by definition, a does divide 2b squared minus 3b. And we are done. Okay, so let's do another proof using the definition of divides. So now we want to prove that if a is an integer and 3 divides 2a, then 3 also divides a. This one's a little bit trickier. I'd like you to think about it for a minute yourself. So think about it for a minute, and then I will give a hint, and then think about it for a minute more. Okay, so if you've thought about it for a little while, the hint I will give is that you can use a previously proven result. So in the first part of the Chapter 4 homework, you showed that if x and y are odd, then x times y is odd. So you might use this in your proof. Okay, so we want to show that if 3 divides 2a, then 3 divides a. Since this proof is a little more complicated, we'll keep a piece of scratch paper on the side. And these are ideas that do not go in the body of the proof. One thing we want to include in the scratch paper is our goal. So our goal is to show that 3 divides a. That is, we're trying to show that a is equal to 3 times t for some integer t. Okay, let's start our proof. So in our proof, we're going to assume the hypothesis. Suppose that a is an integer and 3 divides 2a. Now let's expand what it means for 3 to divide 2a. So since 3 divides 2a, that means that 2a is equal to 3 times c for some integer c. So for some c in the integers. So at this moment, I'd say the next step is not totally obvious. So we know that 2a is equal to 3c. Is there anything that we know at this point? Well, we know the definition of an even number. We know a number is even if it's equal to 2 times an integer. So 3c is equal to 2a. That implies that 3c is even because a was an integer. And now we could use the hint that I gave. So we know that we showed that if x and y are odd, that implies that x times y is also odd. Again, you proved that in the previous homework. So let's use that over here in our proof. Since 3c is equal to 2a and a is an integer, that means that 3c is even. 3c is even. We know that 3 is odd. So if c is also odd, then 3 times c will be odd by previous results. So c must be even. Now we can use the definition of what it means for c to be even. So since c is even, c is equal to 2k for some integer k. So let's think back to what we're trying to prove. We're trying to show that a is equal to 3t for some integer t. So we want to know more about a. And we do at this point know more about a. We now know that 2a is equal to 3c, and 3c is really equal to 3 times 2k. And so dividing by 2 gives the expression a is now equal to 3k, where k is an element of the integers. And so what does that mean? That therefore 3 does divide a because a is equal to 3k, and that's exactly what we wanted to prove.